34.85% efficiency. That number just broke a law of physics. Iron rusts. A battery runs for 100 hours. 2 ancient materials. 1 future nobody predicted. The quantum leap. Iron rusting is the oldest chemical reaction we ever used. Here at the quantum leap, real science shows you the world it builds. Every scenario here is built on real research and data. Imagine 2035. Your city runs on iron and crystal. No power company bill arrives. The grid pays you instead. The question is not whether this happens, it's how fast. The silicon solar panel has a physics problem. The Shockley-Queisser limit caps silicon efficiency at 29.4%. Silicon catches only half the sunlight hitting it. Researchers had been looking for a solution for 30 years. The answer was hiding in a Russian mine since 1839. Perovskite, named after Russian mineralogist Lev Perovsky. It catches the light silicon misses, blue and ultraviolet. Stack it on silicon, and you break the fundamental limit. The theoretical maximum for perovskite tandems is 47%. But efficiency records in the lab are not commercial modules. Perovskite degrades in moisture, oxygen, and heat. The stability problem blocked commercialization for 15 years. Then, in 2025, a team at Manchester found molecular glue. Professor Anthopoulos called the molecules imidinium ligands. They act like structural glue, holding the perovskite lattice together. Published in Science, peer-reviewed, results replicated independently. The cells retained full efficiency for 200 continuous hours. Simultaneously, in January 2026, Xian Jiaotong published another approach. Molecular press annealing, a fundamentally different stability path. 2 different solutions to the same problem, both published within months. The stability problem was not solved, it was solved twice. Now let's look at what happened in the market. Oxford PV shipped first commercial modules to U.S. utilities in September 2024. 24.5% efficiency, certified, shipped, and installed. Perovskite is a crystal discovered in a Russian mine in 1839. Stack it on silicon, and you break the fundamental physics limit. Longi just hit 34.85%, NREL certified, in April 2025. Oxford PV is already shipping commercial modules to U.S. utilities. Hanwha Q cells passed IEC and UL certification in 2026. For the first time, a perovskite panel passed industrial durability standards. Perovskite can also be printed like a newspaper. Silicon requires energy-intensive crystal growth at 1,400 degrees Celsius. Perovskite films form at room temperature with simple chemistry. The IEA projects perovskite reaches sub-retail pricing in 5 years. That's when more panels generate power than you can use. But cheap solar creates a new problem. What happens after sunset? This is where the second strange material enters the story. Yetming Chiang co-founded Form Energy at MIT in 2017. He had a radical insight: iron rusts. What if that was reversible? Discharge: iron oxidizes, takes in oxygen, releases electrons. Charge: apply electricity, reverse the reaction, derust the iron. The result: a battery that stores power for 100 hours. No thermal runaway, no heavy metals, no fire risk. and it costs less than $20 per kilowatt-hour. Lithium-ion batteries cost more than 10 times as much. The sun generates clean power, but only a quarter of the time. Storing that power required lithium, a geopolitical choke point. Iron-air batteries use iron, water, and air, no lithium. Form Energy built their factory in a former West Virginia steel town. The same iron industry that built America now stores its energy. Why this breaks the lithium dependency? The data is in the contracts. Xcel Energy and Georgia Power placed the first commercial orders. 3 iron-air systems come online in 2025 and 2026. But then Google made a move nobody anticipated. 300 megawatts, 30 gigawatt-hours, Pine Island, Minnesota. The largest battery project by energy capacity, announced globally. This is not a pilot project, this is infrastructure. Then in March 2026, Crusoe AI signed 12 gigawatt-hours for data centers. Nobody predicted AI data centers would validate iron-air economics. Form Energy now has 75 gigawatt-hours of commercial agreements. So far these look like parallel developments. What if they aren't? Here's what changes when both technologies hit economic thresholds simultaneously. Every renewable storage solution requires lithium. China controls 80% of refining. They exist because solar and wind can't power cities after dark. Iron-air storage at 20/kWh runs for 100 hours, continuously. Perovskite solar generates the cheap daytime power to charge it. Together, they eliminate the economic reason peaker plants exist. This is the cascade, and no single industry is ready for it. The full convergence data, in which plants retire first, follows. Gas peaker plants are the most economically exposed first. They operate below 15% capacity annually at maximum cost. Their effective cost, $200 to $500 per kilowatt-hour of available energy. When iron-air storage reaches grid-scale deployment at $20 per kilowatt-hour, gas peakers stop winning bids in electricity markets. They don't shut down overnight. The economics simply strand them. This is how the Industrial Revolution ended, not a detonation, an abandonment. But the cascade doesn't stop at gas peakers. Cheap solar plus cheap storage changes the entire grid economics. Natural gas peaker plants cost up to $500 per kilowatt-hour of available energy. Consider what happens to utilities when their backup infrastructure becomes obsolete. Would you invest in new gas infrastructure today? The data suggests fewer are. Meanwhile, the geopolitical implications are becoming visible. Iron-air batteries are made from iron, the most abundant metal on Earth. Countries that import oil suddenly have domestic energy storage materials. The IRENA 2026 analysis, Energy Transition Reshapes Trade Relationships Fundamentally. Weirton, West Virginia lost its steel mill and its economy together. Form Energy built their factory on the same industrial site. They make batteries from iron, the same element as steel. Same hands, same skills, entirely different future. This is the human scale of the energy transition, not hype. Why this matters beyond energy, and what it signals for industrial America. One important limitation: this timeline has seen failure before. Perovskite has been almost commercial for a decade. Technology timelines in energy are notoriously unreliable. What's different in 2026 is commercial contracts, not laboratory records. Oxford PV modules are on U.S. rooftops now, not in a press release. Form Energy modules are charging from Xcel Energy's grid, now. The workers making tomorrow's batteries learned their trade making yesterday's steel. Now consider what the full convergence actually means. Cheap generation, multi-day storage, no critical mineral dependency. So what does this convergence mean for the next 30 years? It's 2038. You haven't paid a power company bill in 3 years. Your home battery charged overnight from yesterday's solar surplus. The power company pays you now. The grid needs your surplus. Your grandchildren will ask why electricity ever cost money. That's the future the science points toward, but here's the honest assessment. Perovskite modules are shipping, but at 24.5% efficiency. The 34.85% record is a lab cell, not a commercial roof module. AI training runs consume electricity at unprecedented scale. March 2026, Crusoe AI signed a 12 gigawatt-hour Iron Air deal. Google signed 30 gigawatt-hours for their Minnesota data center. The technology replacing fossil fuels is being validated by artificial intelligence. This creates a reinforcing cycle neither technology could achieve alone. The full second-order consequence cascade, the one nobody planned for. When perovskite solar reaches sub-retail pricing, expected within 5 years, and Iron Air achieves grid-scale deployment at target cost, the business case for new fossil fuel infrastructure simply disappears. Not through regulation, through pure arithmetic. The last generation to build coal plants has already been born. They just don't know it yet, and neither do the oil companies. Here's the framework for watching this unfold. Track 3 signals. Signal 1. Perovskite commercial module efficiency crossing 30%. Signal 2. Iron Air deployment exceeding 10 gigawatt-hours annually. Signal 3. First gas peaker plant retired due to Iron Air competition. All 3 signals are now within a 3 to 5 year window. Nobody predicted AI data centers would become Iron Air batteries' first major market. The pattern of industrial transformation always looks inevitable afterward. We're at the moment before it looks inevitable. That's why this matters. This channel's value is connecting what other channels cover separately. A materials scientist and an energy economist rarely read the same journals. The convergence between their fields determines which version of 2035 we get. In one version of 2035, both technologies scaled, the cascade completed. In the other, manufacturing bottlenecks and grid investment delays stalled the transition. The difference comes down to manufacturing investment decisions being made now. The science exists. The question is always deployment. Dr. Yetming Chiang spent years building the battery nobody believed was possible. He comes from MIT's materials science tradition, the same tradition as lithium-ion. John Goodenough published the lithium-ion breakthrough at age 57, Nobel at 97. He spent 4 decades watching his invention reshape civilization. Somewhere now, a researcher runs the experiment that determines your energy future. You won't know their name for 20 years. The rust and crystal will.